Okay, get started. Am I good for recording? Cool. My name's Shannon Jocelyn. I am I'm a PhD student in the Integrative Genetics and Genomics graduate group, and I'm affiliated with the Brown Lab through trainings and just kind of hanging around. Thanks for coming to my talk, or to the MAD session today. But we're going to talk about project organization and management. And so the first 20 to 30 minutes is we're going to pull from some data carpentry lessons on project organization and management. And then the second half of the hour, I'm going to show you some slides and some tricks that myself and a couple other people in the room think about when they go to organize their project, or just when they think about their projects more loosely in general. So before I get started, any questions? We're going to go to the first URL to begin with. So when we're planning for a next generation sequencing project, there are a few questions that we want or ask ourselves. First is, how do I plan and organize a genome sequencing project? And then another one is, what does a sequencing facility need, and what are guidelines for data storage? This is kind of, when we think about these things, it's, okay, well, how do I manage my workflows, and what kind of information am I actually going to have, right? We're used to storing reagents. We're used to storing pipette tips. Those are physically tangible. We can manipulate them with our hands, and it's a little harder to think about when we just have a flat screen in front of us, especially when we have something like the terminal blinking in front of us. So hopefully we'll be able to, by the end of this lesson, we'll get a little bit more in tune with how to kind of take the flat screen and make it more manipulatable. We can manipulate it in our minds. Sorry, I haven't really talked all day, so I'm just warming up with chatting. Yeah, and then guidelines for data storage. So the sequencing data that we acquire, we could store it in one location, but we might think about, well, if that one location goes down, we wouldn't have our data anymore, so we'll think about different ways of backing up data. We'll also understand the data that we send and get back from the sequencing center, how to initially understand how we pull that data off and make sure that we have indeed downloaded the full file, which is really important when we're downloading large data sets, because how many of you guys have had issues with EduRoam ever? Right, yeah, so internet connections go down sometimes. That can happen while you're downloading data. It can happen one sequence letter before your data is done downloading, and then that's your full data set. So we'll think about that and make decisions about how and if data will be stored, archived, and shared. So any questions before we started? All right, so yeah, there are a variety of ways to work with large sequencing data sets. How many of you guys have already started a bioinformatics project? Okay, and then how many of you guys are looking to start one? Awesome. Okay, so hopefully this will be useful for both of you. Not only if you're just looking to gear up to start a project, but if you're kind of in the mix of it and you can develop a few more best practice type techniques throughout this. So we're going to have a little discussion between, if you turn to the person that's sitting next to you, we want to ask some questions. So if you're at a workshop, we're talking about working with sequencing data. And so if you could talk about the 4 questions, what challenges do you think you'll face? Or if you've already had a project that you've already faced in working with large sequence data sets, what is your strategy for saving? And actually, we're going to divide this into rows so that we have enough time. So maybe the back row, talk about the first two questions. What challenges do you think you've faced or have already faced with working with large sequencing data sets? And what is your strategy for saving and sharing your sequence files? And then the first two rows, how can you be sure that your raw data have not been unintentionally corrupted? And where and how did you analyze your data, and what software and what computers did you use? So we'll take a couple minutes to talk about that, maybe until 3:18. Yeah, so you can introduce yourself.
Yeah. And I think that's
I'm trying to learn Unix, so I'm trying to learn this thing. And they use Docker. They use Conda. And you can install software. I was able to train my data and do some it's good.
Okay. So, try to have everyone's attention again. So everyone has lots to say. That's very good. So someone from the back, what are some challenges that you faced with your sequencing data?
Naming and keeping notes about what you've done.
Yeah, notes.
Easy way to get back to them and understand that.
Where and how? Yeah. Any other challenges? Backup. Backing up data. What about saving and sharing sequence files? Anybody have any strategies for sharing and saving sequence files? Clusters? Yeah. What happens if the cluster goes down?
I don't know.
Yeah.
I cry.
Good, bad. Clusters, our savior or our foe, who knows? What about corrupted data? Anyone from the front even thought about corrupted data at all? We have big files with lots of letters. We just do science with them. So there are ways of checking to see if when you say download data, you can check to see if your data file has been corrupted. We'll learn about this. It's through MD5 sums. Basically what it does is it says, I've generated a string of letters and numbers that's very specific to this file when it's in the first location, and then you've downloaded it, and you can generate that same sequence of letters and numbers, and if they match from where you've taken the data to where you put the data, then your file is hasn't been corrupted, and it's the exact same as the place that you pulled it from. And then what about, where are people analyzing their data? On their personal computers or clusters mainly? Anyone using anything else? AWS?
Jetstream.
Amazon Web Service or Jetstream? These are all places that you can go to analyze data. Some of them you can store long-term, other ones you can't, but there are multiple places. The cluster isn't the only place, and you can do powerful science even on a not so powerful computer if you have resources. So before we go into the project organization and management, we'll just talk briefly about even sending samples to the facility. So the first step is sampling whatever study species and that you'll be sequencing, right? And you probably have to complete some type of form documenting metadata for the facility. So if we could all click on this sample submission sheet, this is a sample submission sheet for a sequencing project. And so the submission to the sequencing center might require certain well positioned. The first one, this is kind of small, make it bigger. So the first column is well positioned. This is someone who submitted a plate to the sequencing center. So well positioned, and then you might have the two barcode, which is this series of numbers. You might have a plate barcode, client sample ID. All of these different sequencing centers have different submission information that they would like to get from you, and it varies based off of what kind of sequencing you're doing. If you're doing an RNA seq analysis, you'll probably have a different form than if you're submitting for genome assembly. And so that's something that is individual to each sequencing center. How many of you guys are not using the UC Davis Sequencing Center? Okay, cool. So I'll have the link to their submission form, and we'll get to that in the PowerPoint portion of this presentation. Okay, so going back to, you can download this data if you'd like by right-clicking. But let's just look at it here. Can anyone find any kind of immediate errors in the data? If you downloaded it to your computer, it might be easier than just looking up here. Yeah, the date format is different at the bottom of the file, right? Yeah, so it shifts right here. So that's something that you wouldn't necessarily want to have, right? Because let's say that you were gonna run some kind of analysis looking at, oh, is date a factor for what I'm seeing in my experiment? Well, you wouldn't be able to compare 6 July-15 to 7-/8 that easily. So something that we'll be saying all throughout this MAD session is just consistency is key. So it's consistency in like what you're saying, naming files, in the way that you run scripts, in the way that you handle metadata. It might be, let's say that you have 96 individuals. That could be really easy to go through and look at an Excel spreadsheet of 96 individuals and look at all of the tabs and kind of have a good sense of your data. But when that expands to 32,000 individuals, it becomes harder and harder to do that. So consistency is key. And then, so question number 2, what improvements could be made in choices in naming? So let's see, column for the names, client sample ID, have this wild type, and then we have wild type, and then we have K255N. So what might be a better naming scheme for these? Yeah, no spaces. How do you guys work with R? Spaces become a thing, right? You try and load like R might think, okay, well this is one column and this is one column and this is one column and then this wild is one column. So then it's grouping wild with this K255 underscore 1H-1, and then it groups type with A, and then all of a sudden you're like, oh my gosh, I don't know what to do with all of that because half of my file is loading in one way and half is loading in another. So in a lot of in all of NGS projects, in all of bioinformatics, white space is really key. And so whenever you have kind of 2 words that you want in one column, push them together into one. So we have wild type here as one word. That would also read differently from this line. So something to think about when you're putting together your spreadsheets. And then what are some errors in the spreadsheet that will be difficult to spot? We've already kind of talked about this, but what's difficult to spot? The white space is one, right? Just the fact that at one point you're calling samples wild type, and then they have this really unique name down here. you might want your wild types names to like vaguely match this, but it depends on your project. But it's something to think about. Yeah. So you can look at the solution. Right, so errors are the sequential order of well positions. We've already gone through a lot of this. Format of client sample ID, capitalization, replicate column changes, volume and concentration column headers, volume, concentration, and RN column decimal accuracy changes, the prep date and trip date. Formats are different, and the prep date has multiple formats. So I'm not going through this just to like read to you, and I'm just going through this because there were so many things that we didn't find just on an initial pass of looking at the data, right? So like even if you think that your data looks pretty good just by eye, there are so many things that we don't catch. So the more standard and the more we can automate things to do the same thing and we don't have to do that, the better. So yeah, something to think about. So then when you go to, so let's say that you've submitted your sequence or your samples to the sequencing center. You provided nice clean metadata that doesn't have any of the errors or inconsistencies that we were talking about. Next, you want to retrieve your samples from the sequencing data facility. And so you might get some sequencing results that look like this, but so if you download and examine the following example file, So these files right here, you can download them. There you go. My computer is being slow. Actually, since my computer is being slow, do you want to turn back to the partner that you were talking about the first questions with? And we'll do the back row goes through, actually, the back row on the wall can go through questions 1 and 2. The next row up can go through questions 3 and 4. And then row 5, or the first row can go through number 5, and then you can pick a wild card 1 through 4. Just go through 2 questions. We'll chat about this at 3:34. Sound good? Okay, cool.
Oh.
Size the read.
Okay, so can anyone tell me how the files are or how these samples are organized? Look here. Anybody? Yeah. First column? Yeah, looks about right. Yep. So because these two have the same sample ID, so then they're organized by this R1 and R2, or the forward and reverse reads. Yep. And then if you wanted to relate file names to the sample names submitted above, so for example, that wild type that we had, could we do that? If we wanted to relate the file names to the sample names submitted above, so that wild type, or we had those like KRR sample names, could we do that in this spreadsheet here? If we look at this again. By to barcode, right? Yep. 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 And then if we go back to this, and then what are the, I gave this away, spoiler earlier, but what do the underscore R1 and underscore R2 extensions mean in the file names? So right here and here. So yeah, forward and reverse reads. So we see here that, back up to the top, we have paired end sequencing. And so those are the forward and reverse reads. Do we know which one's the forward and which one's the reverse? Like, is R1 always forward and R2 is always reverse? No, they're just opposite of one another. So be cautious of, or just know. And then what about the GZ extension on the file names? What does that mean? So GZ means it's a zip file. So it's easier to send smaller files. So we have compressed data in those files. So they're all compressed using they're zipped, basically. Has anyone ever gotten like a zip file and then they have to unzip it? Yeah, it's the same thing. And then what's the total file size and what challenges in downloading and sharing these data might exist? So what's the total file size of this link? Here. Oh, the total file size. Oh, okay. Yeah, we could do that. Yeah, the total file size of all of, oops. Let's see, it's 1,113.6 gigabytes. So just over a terabyte. I know you guys have a terabyte just open on your computer. I don't. So we probably wouldn't want to download these onto our computer, but this might be something that we would get back from a sequencing center. We also might not get anything this nice back from a sequencing center. If you've gotten things back from the DNA Technologies Core, they just kind of say, your data's ready. And that's kind of it. And then they give you a link, and that link contains a lot of folders that you click through, and you're like, well, what do I download, right? Yeah, so you can find the solutions here if you want to read about them, but we went through that. So next we would think about, since we were just thinking about not having a terabyte of data on our computer, is storing the data that we get back. So basically we would get back raw sequence data, and that's kind of like the holy, that's like the gem of your project, right? And so there are a couple things to think about when we get that. First is, did we download all of the data, right? So that's going back to that MD5 sum that we were talking about earlier. The next thing is, okay, well, once we have it, how do we make sure we don't ever change it, right? Because I don't know, how many of you guys saw that I changed one of these file names? Taylor did. I can't even find it again. Oh, here it is. Okay, error here, right? So I changed this. This could have also been, I could have changed it by one by one letter, and the letter could look the same and I would never know, right? So I'm editing this file. We can do the exact same thing with our sequence data files, and we never want to do that. So there are some general practices that we have for storing data. One is kind of going back to where we store it, is that we want it to be accessible by not only ourselves, but other members of our lab, at least the PI of the lab. And then if you're gonna have an open data set, maybe we want more than just our lab to be able to access that data. And then two, we want to store the data in multiple places, so it's redundantly backed up. At least 2 different locations in 2 different physical areas. So that could still mean that we don't have a hard drive. It could mean that we store it in 2 different data storage services. And yeah, we also want to leave all raw data raw. And so we're going to go into some file permissions. And if you have if you're working on a cluster, how many people are working on the farm? How many people have so I guess that's a couple. Is anyone working on Cabernet and then clusters or Crick? What's Crick? Oh, it is. Okay, cool. Do they back up data on there? Right. So neither does the farm. So we want to make sure that we have backed up our data in places. So yeah, we can use places like AWS or Amazon S3, Microsoft Azure, Google Cloud, and if we don't have that much data, we can use the Open Science Framework. So we can store up to 5 gigabytes of data. And there's another data carpentry lesson if you're interested in that. But if we go back to our slides, I just kind of want to play around with more of the things that we've touched on, like MD5 sum and how a few of us think about data organization in this room. So if you want to follow along with the slides, you can go to this GitHub right here and download all of what we'll be sifting through, including the slides for this. So we're going to talk about sending and receiving samples. We've already kind of done that, as well as storing data. But then more importantly, is setting up our project and working with the data. So sending samples to the facility, we kind of touched on this before, but here's just the link to the DNA Technologies Core sample submission forms. So you can see how this one's a little bit different from before. Let's say we're submitting here. Hopefully it will open. Come on. All right, well, my Excel is being not that great. But there are also, so if you're submitting 10x data, for example, you create a submission form and then you have to go through and fill everything out. And so this also, there's errors that you can introduce here when you go to add your samples. So just be really careful that you don't want to have errors. Yeah, so you'd go there to submit samples. And then retrieving the samples, sequencing data facility. So the UC Davis DNA Technologies Core uses the SLIMs. So here's the link here, and they'll send you an email once your sequencing is complete, and you use, I think it's your Kerberos login, and you log in here, and then you can have access to your data. However, this is something that's said in the emails, but they only they only keep your sequencing data on there for a few months, so you can't use it as a long-term storage space. So that's something to be wary of. But so we talked a little bit about MD5 sums. So if you wanted to run MD5 sum on the file, the command is MD5 sum, and then we type the file name. So if I go to my computer and let's see what kind of, where am I? Okay, so I have some files here. So this is the slide, the slides that I have for this talk. And so I can generate an MD5 sum for any file. I could generate it for this PDF file. I would type MD5 sum and then the file name, and it spits out this long string of letters and numbers. And this is what you want to compare between files. Really, you only have to look at the first 6 or 8 letters, and you'll know if you have the same file, because even if one thing is shifted, you'll notice that difference in the MD5 sum. So it generates a string, and then it gives you the file name on that side. So I could do that. Let's say I wanted to do that MD5 sum for anything that ends in, I only have one of these, but .md. So that would grab an MD5 sum for this readme.md. So it's really useful when you start having a lot of files that you're going to be downloading, and you can put this into a list. And you can put it in a list in a file, and then you can do this MD5 sum -c in the file with a list of MD5 sums that you have. And that will allow you to check multiple files at one time. So if I were to do this, let's say I'm just going to create another one of these. So I'm going to copy, oops. I'm going to copy this README. And I'm going to call it README2 MD. Right, and then I'm going to MD5 sum all of my .md files. Oop. So that gives me a list, right? So I can put this list into a different file. So I can say MD5 sum all of my MD folders. And then I want to put that into a checksums.txt. I hit that, and then if I were to look at this checksum.txt, I see that it's that list that I generated before. But the cool thing is, so if I have this checksum in the same directory as those two MD files, so we can look at ls-l, and I can see, okay, it's in the same directory as these two README files. I can do MD5 sum -c, and then I can type in the checksum.txt, and it'll tell me if all of my files are the exact same. This one, we haven't downloaded anything, like I created it in the same directory that I tested, so obviously we wouldn't think that it was, but let's say that I change something in this. So I'm just going to change, I'm going to delete this one thing here, and I'm going to run this MD5 sum check again. So I only changed one thing in this file, and I'm checking it. and then I get that it failed. It's because, even though there were multiple different letters and lines in that one file, that one difference gave it an entirely different MD5 sum. So that would fail, right? So if we were downloading, whenever you get sequence data back from a sequencing facility, this is something that I wish that just came automatically with sequencing data, but you can always ask the sequencing facility to send you an MD5 sum, and please do. They won't necessarily do it automatically. I've had to ask in the past, but then you can just go through and check all of the MD5 sums and see if you've downloaded them all correct, without any corruption. Yeah.
What happens if you have more than 2 files? Like, what is it comparing? Like, if you have 4,
Yeah.
is it comparing like?
So it's never comparing between. Like, it's not comparing readme MD to readme to MD. What it's doing is it's saying, so let's look at this file. So it's taking, it's in the way. It's taking these 2 files and it's generated a string of letters and numbers that's attached to that file name, right? So readme.md will have that MD5 sum, and so if you copy readme.md to even a different place on your computer, a different directory in your computer, or you send it to a friend via email or a collaborator via email, they can take this string here and make sure that that readme.md is the exact same file on their computer. And then, you have 2 readmes in this one, so they can make sure that the second file is the same on theirs as well. So
It's actually running the checksum, but then checking it in that file.
It's checking it against this file. Yeah. So if we were sending our this file to a collaborator, we would send them this, and we would send them 2 README files, and then they would do MD5 sum-C and give them the checksum file.txt, and it would make sure that those 2 files were downloaded correct. Yeah, or without corruption. Does that make sense? Okay, so it's a little silly doing it with these READMEs. What it would make sense is if we have 3,000 sequence data files. And remember that list that we had, and we have the file size, and the file size could seem the same, but if one base pair is changed, we wouldn't catch that just on file size. We could catch it for MD5 sums, or with MD5 sums. Yeah, so this is just a little bit about a couple of the services on campus. So working with data just on the farm, so it's managed by the computer science and engineering systems and cluster support, and here's some links to the documentation. And then the Jeffrey Ratsabara lab also has documentation. There's also Cabernet, which is managed by the UC Davis Bioinformatics Core, and they have a training just on submitting to their cluster. And we always want to back up our data, and so Louise is going to give a tutorial next week on backing up data. So I'm not going to focus on backing up data so much as I'm just going to kind of chat about things to think about other than backing up data. Yeah, and so like Taylor was saying, there are other places we can go to work with data. So Amazon Web Service is another one. Jetstream. Those are both. Actually, is Jetstream? I don't think Jetstream is linked on the Data Carpentry's website. So I will update this slide to include Jetstream. But there's also the Google Cloud that I guess you would go there to store data, but you can go there for a few other services. So the next thing that we would think about with our data is how we cannot mess it up. And so we always want to change our raw data permissions using this mod command, or change modifications. And so who knows about permissions? Okay, so basically permissions are who can access files, who can access the file, who can write on the file, and who can execute the file, right? So we might have some files that are executables, they're scripts that will be running, and then we'll also have ones that we'll want to be able to change, right? So I might want to change my README file, but I never want to change my raw data file. So if we go into projects, and then an E delta smelt, and then go into data, like ls-l, and so the permissions, and so who can read and write and execute the files are located on this column here. So you're the first person. The first three, well, after the first dash, the first three little dashes are what you can do to the file. So this is saying I can read the file, I can also write to this file. It's not an executable file. And then it goes to the group that you belong to. So how many people, or of those of you who work on the cluster, you belong to a group, right? And that group is probably your PI, because your PI may have bought into whatever cluster you're working on. And so all of the members of that group can have certain access to your things that maybe everyone who's working on the farm or Cabernet don't have. So that's the next three little dashes here. So you have read, and then they can't write, and they can't execute these files. And then the last three dashes are all of the members that are on whatever cluster you're using. So I'm a member of the farm. I'm probably not associated with your lab. Can I go through and read to your your file? Yes, I can. Can I write to it? No, I can't, but I can read it. So here we have a bunch of fake sequence data files. I say fake because I just created them. They don't actually have anything in them. But so we're going to treat these as raw data. And so right now I can write to them. So I can go in any of them. I can dash a few things on my keyboard, and then I can save it, exit, and no one would ever know. But we don't want that to happen. So what we would do is we could look at our command here. So the chmod, we type chmod all equals R. And so what this is saying is that I want everyone to only be able to read this file, or these files. And I can type in individual files. So I can say this individual file. And then if I were to list out all of the files again, we see that this bottom file, now we can only read the bottom file. We can no longer write to it. But if we want to do it to all of them, who knows about the wildcard key? Yeah, so we can use wildcard. So all equals read only. And then we can use the wildcard. And then dot FA. So basically what this wildcard does is it says, sorry, having some water issues. It says, expand this character before .fa for as much or as little as possible, right? So I want to expand it. You can see here that these are different sizes, the SRR 0, some string of numbers. They're different sizes, but I want to apply it to anything that has .fa at the end. So if I hit that, and then I type ls-l to look at those files again, you can see that they're all read-only, right? Change. Cool. So that's just really key to do immediately once you've checked that your files are, I mean, you can do it before you've checked if your files are corrupted, but I would say those two things are the first things that you do when you get sequence data back. They're very important, just so you don't alter anything that you interpret to be biologically meaningful that's actually just a product of error. Yeah?
You can do this for other files as well?
Yeah. Yeah, you can do it for any file. So if you had like a private file, let's say, sensitive, yeah, you could do chmod, and you could do let's see, group -r, and then give this name type LSHL. So then you know, your group can no longer read your file. So that becomes a more private file. I don't know how to. You know how to get rid of the all users, but not yourself? It's O. So we could do the same thing. So chmod O-R and this file. And then when we look at those files again, we've now made this file only readable to myself. So other, thanks. Yeah, so you can have like sensitive notes on there or any information that you don't want anyone else accessing. You can keep it private to yourself that way. I should have done this earlier, but for those of you who haven't done this yet, if you clone the GitHub directory, do git clone and then type this link out, https:// I'll let you read it. Okay, so okay, so you'll have something that looks like this, right? And so if we go into the O directory, and then we type ls-l, we see a bunch of SRR sequence files, and then we see this align.sh and this splitreads.sh. We might scroll up for a while, and there's a lot of other things, and it's all pretty messy, and we're not too sure what's coming from where or what anything really is. There's this pca.sh, and then there's this run pca.sh. And so it's kind of, how many people would like go into this folder and be really excited about it, having everything all in front of your face? Not really, right? But it's like all in one place, like thinking, okay, that's great, all in one place, project, project. But we don't really, we don't get a good grasp of, if I just type ls, it looks like I just have sequence files and then I have these two bash scripts here, which is not the case. It's just that I have a lot of sequence files and I have more than that, but we don't get a good grasp of that. So we might think about, if we go up a directory and type ls, we might think about how we could structure our directories and files a little bit differently in order to allow us to kind of organize those things. So if I go into projects, I no longer have an O project, but I have these 4 different projects. So these are 4 different projects. What's immediately apparent about these projects that I have here? Well, may have been an insufficient question, but these, so we were talking about consistency in file names. I also like consistency in project names. So if I do multiple types of genome assemblies, for example, which is what I do for my work, I have this, the first word is genome, and then I have the study species that I'm assembling the genome for. Again, another thing I work on is effective population size, or we shorten it down to NE, and so I have NE and delta smell. This is a good way of just kind of thinking about, oh, how many genome projects do I have? Well, I know that these are my genome projects, and they're all kind of named the same way. We don't always get that. Sometimes we get, we're working on software, and that just might have one name, or we might be working on something that someone has already named, but it's good to think about just in consistency. So if we go into one of these genomes, genome projects, can anyone think about, okay, we have our project. We're working on assembling the genome of milk smelt. What might I have in that folder? Can anyone think of things that we might have? A raw data folder? Yeah, that's great. Yeah, right. We want somewhere to keep our raw data. It's good if it's somewhere other than just out in the open. We're probably going to run some scripts on it. So we might have a scripts folder. We might have a metadata folder, right, for all of our metadata. We could also have an output folder, right, because we're going to be generating a lot of output. So if I type ls-l, I can see here that I have an analysis directory or folder, a data directory, an output directory, and a scripts directory. And if I look at my README, I can see kind of what's going on here. So someone said before that, I believe someone said before that they were thinking about how, what was it? How, where, and how to keep notes, right? So README files are really great for keeping notes, right? Because you can go into a directory and you can know exactly what's in the directory based off of what's in your README file. So here, this is in my genome_delta smelt directory, and I have this README, and it says this is a repository that contains scripts used to assemble and analyze genome delta smelt, blah, blah, blah. Data, so the sequencing data, what kind of sequencing I did, 10x genomics on one female fish from FCCL captive colony, that's just where we kept the fish. And then I also have some organizational things, so I have scripts And these are scripts that I use repeatedly. So they're scripts that I might call on to do a certain function over and over again. I will also say that this is how I organize things, how Louise, Taylor, Tessa organizes things would be vastly different. Maybe not vastly different, but subtly different. I don't use SnakeMake. I just don't know how yet on the to-do, but I don't use SnakeMake. So, and I know that Louise and Taylor and Tessa all use SnakeMake, so they'll have a slightly different structure to how they organize their scripts and everything. But
Very similar.
okay, okay.
Kind of going on top of it's sort of when
Yeah. Okay. Yeah. Great. Good. Yeah, and then so then there's my analysis files, and these are shell files to call on generic scripts. So I like to have analysis files that I'll edit every time I go to like do a different project. I'll edit it just a little bit, and then I'll call on the ones that I use repeatedly. So that way I'm never really editing my scripts. I'm just editing these analysis files. That's a weird thing that I do, but then there's also output, which is any output, so figures, modified sequence files, stats files, apologies for the typo, and generated by my analysis scripts. So basically, any output that I have from carrying out the analysis, I pop it into this output directory. And so we can go and dig into these files or these directories. I think I can use, I don't actually use this command in regular thinking about directories, but it might be useful in front of you guys. Okay, yeah, good. Yeah, so if we think about, we can see everything that's in these files here. So in my analysis files, I have the process that I carried out the analysis in. So first I ran my divide barcodes script, and then I ran supernova, and then I ran Busco, and then I ran assembly stats. And basically, I like these analysis files to call on these scripts that I use for all of my genome assemblies here. I don't ever change these scripts. They're just nice to have in one container, so I can have it on GitHub, and I don't have to source it from like a home directory or anything. And then I have output. So these are figures that I've created from my assemblies. So these are PDFs, right? And then I have my data files. So these are 5 different data files that contain sequence data that I'd use to assemble this gene, for example. Does this kind of make sense? Does anyone have any like questions on how to kind of think about, and also any like Louise, Taylor, Tessa, Karen, do you have any comments on how you organize data differently?
The one thing I'll add, I mean, everybody looks slightly different as far as like how if they have inputs or where they put their outputs or whatever, and that's not terribly important. But one thing that I really love to do is have a sandbox folder. So if it's like a half-baked analysis that I want to try and I'm trying it on my data and I want to keep track of everything I ran, I'll put it in my sandbox folder, maybe in its own folder named like DEC if I'm trying that, especially on my data. And then I'll try it and have a record. And until I know that I'm going to use it, I don't formalize it all like this. But then I definitely always do go back and formalize it once I actually am going to use it and it comes out of the sandbox back into the.
Yeah, that's great. And so that's really useful if, say, she was going to generate output that she put in here, but she was also going to maybe have another analysis script here. So if it didn't work out, she wouldn't have to go into all of those directories and delete all of the things that she didn't like. So sandboxes are fun. Yeah.
Do you recall you are looking?
What's that?
The recall you are looking for. For example, yesterday you did some analysis about the PCA, but today I want to achieve some parameters and redo the analysis. So how do you
Can you record that?
Yeah.
Yeah, so I mean, if you, let's say that you wanted to run assembly, let me know if I'm getting this question right, but you wanted to run assembly stats and you wanted to see what your assembly statistics were with specific parameters, right? And then let's say that you wanted to change that the next day. You could make assembly stats 1 and 2, or you could give it a more descriptive name, which I like, which is, let's say you're doing assembly stats and you wanted to run, you're looking at k-mers in your assembly, and you're looking at like a k of 31. And then the next day you wanted to run assembly stats with a k-mer length of 27. You could put assembly stats dot k31, and then the next day you could copy it. You could say assembly stats dot k27, and then edit that script to have a different k-mer length. That's a good way of having both of those analysis scripts in your in your file or in your directory, and keeping attached to them. Generally, I don't ever take a script and run it, keep the data, and then change something in that script and keep that data as well. I always have 2 different scripts that, so I can know the exact parameters that were run on my data. The same for softwares and everything. Just, you always want to keep a log. So better to have, 2 different run assembly stats files than just one, and confusion, when you come back to it in a year. Okay, yeah, so keep track of what you're doing. README files. Sorry I'm running late. Consistency is key, so naming files, try and keep your name similar. So if we look here, these SRRs are all similar name, right? So I could perform functions on anything that has .fa, or I could perform functions on anything that has SRR that is trailed by anything else, right? So that's super helpful. If those were all named all crazy, I had one that was, x5.txt, that would be weird, and I wouldn't necessarily pick it up as a sequencing file. Directory structure, and run scripts. So have scripts that you can use multiple times. And so tricks for making your project repeatable. So so here I have where these are my scripts, analysis, data, and figures are all located on my computer here, and this is the global path, right? So I have Pliocene, Shannon EKJ, desktop work, GitHub, any Delta Smelt figures, which is one, really long, but even more importantly, only specific to my computer, right? So that's where I downloaded that data to. And that wouldn't be the same if I sent that to a collaborator. So a better way to think about where your data is located is by using relative paths. So I could say to my collaborator, go into wherever you downloaded NE_Delta Smelt and run these scripts, and they call on the relative path. So you could go into scripts and run, let's see. So, sorry. We go into analysis and we run this divide barcode script, right? We say, depending if we're working on a cluster or if we're working on our computer, we just execute this script here, and it knows, okay, I'm gonna go up 1 level, and then I'm gonna go down 1 level to script. I'm gonna go over 1 level to scripts, and I'm going to grab this divide barcode scripts. I'm going to run that. I'm going to go down one level. I'm going to go up into this output, and that's where I'm going to put all of my output, right? So if you think about it, you can think about when we do that, we essentially create a little cloud or a little bubble around our project, and it becomes functioning within a functioning unit just in itself, right? So this is going down one level, going into figures. Things like that are super useful because then your collaborator doesn't have to go in and edit all of what comes before the NE delta smelt project name because that could introduce error, which we don't like. And then use Conda environments. So Taylor and Louise gave some pretty awesome Conda lessons, and that keeps track of software. You can keep track of software versions, and make sure that you can repeat anything in your project using the exact same software version, or at least know which ones you used. Does anyone have any questions on kind of putting your project into a bubble? No? All right. Yeah, and don't waste your time. If you can, use Conda to install things. Louise gave a good suggestion of creating a file to initialize Conda environments or modules, so you don't have to remember how to do that yourself. So basically, I think this is pretty universal. What I try and do when I go to do any kind of project is make things easy on myself, so I can remember to launch one script, and if that script launched like 1,000 other scripts, that's great. But I might not. I will probably introduce error if I'm trying to do 1,000 things at once. Whereas you can just kind of automate that. And then another big one is to try out your script on a subset of data. So this is similar to what Taylor was saying. She was saying that you could try an analysis in an isolated zone, but I often work with a lot of individuals on things that, and I think, yeah, a lot of us probably do that. You work on a lot of individuals that running the complete analysis will take a lot of time, and I might have, 25 steps in one script to do, and it might fail on step 24. But if I were to only run that same analysis with a subset of my data, so on one individual, or the first 50 lines of all of my individuals, that goes a lot quicker than 4 million lines on 2,000 individuals. So if you can try on it, I would always recommend to try on a subset of data so you just know that your scripts work. And then there are some additional resources that I'd like to recommend. So Bioinformatics Data Skills by Vince Buffalo is quite good. It's a book, it's an O'Reilly book. That's one of the ones that I learned off of. And then Best Practices for Scientific Computing. I believe Titus is a co-author on that one, with like Greg Wilson or Greg White. Yeah, it's great. And then Bioinformatics Curriculum Guidelines toward the Definition of Core Competencies. These are all great reads. And yeah, apologies for going too long. Any questions? Yeah.
When you were learning how to do this, did you just trial and error your way through, or did you start by reading material and getting a baseline?
I trial and errored my way through, and it's been a big refinement process the whole time. And I don't think that ever really stops. You kind of hone in on what works for you, which is why we were saying, we all do it slightly different. Yeah.
It's also kind of the best way to learn, because if you don't pick the book, sometimes you don't know why you're doing that kind of stuff. If you made it wrong before, you will understand why you're saying to do that.
Yeah, totally. Yeah. Cool. Okay. Oops.